In this problem, we're going to be predicting what is a product of a mononitration. Notice that this time we have a structure, the compound has two aromatic rings, both of which have substituents. So if you're doing a mononitration, what is the reagent that you're using them? You're using nitric acid and sulfuric acid. HNO3, H2SO4. This is what you're doing. So mononitration means you're given just a major product. You're installing one nitro group. Same here. That's our goal. So we're going to be determining that major product. So once we know what is that we're doing, predicting the major product of these reactions, let's analyze electronic effects and steric effects to predict that. So in the compound above, this ring has a methoxy group, and the methoxy group is activating. So I'm going to write that down, activating. And it is activating and ortho-para directing. But first, let's establish the type of group, activating. Here, chlorine is a weak deactivating group, deactivating. So if you have just one position, 2-nitrate, you need to pick the place that is most reactive. So it's going to be happening in this ring because this ring is activated versus this aromatic ring that is deactivated. So again, one position only because it's a mononitration, so you need to select the ring that is most activated. Then we're going to be analyzing where and with what position do we install that. We said that activating groups are ortho-para directing. So notice here's a methoxy. This ortho position is occupied, but we can do it here. No, that's another ortho, and para to that is this. Okay, so ortho, this is occupied, this is available, and that one. So next, what we need to choose is according to steric effects. So here is right next to the methoxy. Here I don't have any groups nearby. So my major product is with the nitro group there. So that, let's do strong and it's always smaller. So nothing is going to happen in the other ring because again, it's deactivated. And you're going to have only one. This is a mononitration product. And this is what you're going to be forming. All right. So again, strategy is two rings. Which one is most activated? Test. Comparing those. What are you installing? A nitro group. Where? How is this group directing? And steric effects. So electronic and sterics. Next, let's do the problem below. Again, easy nitration, mononitration. So we need to decide what ring is most activated and in what position do we install the nitro group. What do we have here? We have a nitro group, which is a strong deactivating. And here we have an amino group, which is activating. So now we have these two groups. So deactivating, the substitution is not going to happen in this ring. Activating, so it's going to be happening in this side, one position, because it says mononitration product. So where this group directs ortho-para, so ortho to the amino group, these two arrows, and the para position is occupied already, so you have only one possible product, and it is the same, the two ortho positions, ortho to the amino group are identical. So I am going to install the nitro group here. And you have only that one product. And right. So that's one thing, but let's see if I have another. Let's do another example. Here I have activating, deactivating. And here I have activating, deactivating. So the same strategy, but I'm going to change that. Let's do another example here. And I'm going to say Let's add here a chlorine. And here I'm going to do an aldehyde. So I'm going to write CHO here. That's the abbreviation. Remember, aldehyde is that, right? And your R is all of that. And I'm doing a mononitration, same reagent to be able to compare. Only that this time, in the two previous examples, I have activating, deactivating, but in different positions, activating, deactivating group. Here I have two groups that are actually deactivating. So again, the strategy is similar to what we did in other problems. Deactivating, but this group is stronger deactivating than the chlorine is. And let's write it explicitly. So the aldehyde is that. Remember, resonance effects and inductive effect. So that's a stronger deactivating group than that. Meaning, since this is weaker deactivating, this is going to determine where is the synthesis going. So let's write here, weaker deactivating. And that's the stronger of the two. So that means this ring is more reactive than the other ring. So this is the one that is going to undergo denaturation. But where? Halides direct ortho-para. So ortho to the chlorine or ortho to the chlorine. And this is para. So two ortho positions in para. Now I have three places. Where do we put it? It is mono substituted. So here we don't have anything nearby. Here is relatively close to this two, close up. This is in between the phenyl group and the chloride, so unlikely to go there. And then I have in between these two. Here there's more steric hindrance. That phenyl group is larger, so the nitro group is going to be installed here, and that's your major product. So let's do that drawing. So chlorine is here. So ortho to the chlorine here. Again, we didn't use this ortho position because you were in between a phenyl ring and the chlorine. So too much steric hindrance. So we don't go there. And at the para position is also close to the phenyl ring, but this is the worst. So that is your major product. So again, we have used the same strategy. Reagent, what is your electrophile? The electronic group. Ion, you're installing a nitro group. Analyze the two rings to determine which ring is most activated, or in this case, least deactivated. That's where the substitution is going to go. Analyze directing effects, electronic effects, and steric effects to determine the major product.